Okay. One last thing I want to ask you is that is the solid red line just any continuous and piecewise linear function? What does it have to do with the original function? In what sense is the continuous piecewise linear function an approximation to the original function? Any ideas?
Just a guess, but could it be like each piece is like a linear regression of all the points in like that space?
Good guess. I mean, is each segment something like a linear regression? Actually, this is in the strict sense, it's no, but in the spirit, actually, yes. Okay, so somebody can somebody tell me what is in your mind? What is a linear regression? If you have a bunch of points and I fit a linear regression on the bunch of points, what am I doing? So what is linear regression? Can somebody tell me? Okay, so I'm going to answer the question. So what is linear regression? A linear regression is basically the best approximation of any data you have with a straight line. Okay, so the key word here is the best approximation. So you have to define what I mean by best, right? So in actually linear regression, best means I want to minimize the total squared error. Okay, the sum of squared error, the total squared error. And this is actually what I'm doing here. This is what finite element is doing here. So within all possible, among all possible continuous and piecewise linear functions, I'm choosing the continuous and piecewise linear function that approximates my original function the best. It's a best approximation, okay? So basically what I'm doing is I have two things. Finite element is, first of all, I have a constraints. So the constraint in this example is I want the approximating function. So the approximating function is continuous and piecewise linear. And it is piecewise linear in each element. Okay, so here an element is an interval between 0 and 1. You may ask, okay, so what is the difference between an element in finite element and a volume in finite volume? The answer is there is no difference. Okay, there is not really any difference. It's just a different terminology. Especially in one dimensions, there is no real difference. In multiple dimensions, there are some minor, there are some a little bit more restrictions on what can be an element, and so basically in multiple dimensions, any subdivision of the space can be finite volumes, right? There are a little bit more restrictions on what can be a element, as we're going to discuss in multiple dimensions later, but in one dimension, there is no difference. So in finite element, the kind of finite element we are looking at right now, within each element, the approximating function has to be linear, okay? 2 is that is the best approximation. Okay, it is the best approximation, and in what sense? And well, here in this example, is we are minimizing here is the average squared error. Okay. If you look at the different finite element methodologies, there are many. Okay, you may be looking at different ways to formulate the constraint. Okay, you may not require, for example, you may not require the function to be exactly continuous, right? You still require the function to be piecewise linear, for example, but doesn't require to be continuous. Or you can still require the function to be continuous, but it has to be piecewise quadratic as opposed to be piecewise linear. So you have different ways to formulate the constraint. You also might have different ways to formulate what you mean by a best approximation, right? You may minimize the average squared error. You may minimize the averaged you may minimize the averaged squared derivative of the error or something like that, right? So we're going to be talking about this later. But these two things really encompasses what finite element does. Okay, if you understand these two, you basically understand in a very high level what finite elements is.